So let's talk about one of the most awesome ancient Greek dudes, Archimedes, known for a whole lot of things, lived in the 3rd century BC, and the one that we are concerned about is Archimedes' work on displacement and buoyancy. Okay, so without going into all the gory mathematical details, which actually isn't all that difficult, what we're going to do is talk about a basic concept that's going to help you with this unit here on buoyancy with boat problems, flotation, that kind of stuff. All right, so let's have it. So let's take a look at something here. Here is our beaker, bathtub, whatever you want. Okay, and we're going to have some water, and it could be any fluid, but usually it's water. Okay, now let's say we have two objects. One object is on the surface, and there's an equal object. Maybe an object, by the way, what I'm saying is an equal size. Okay, let's say equal volume. Maybe the object on top floating would be wood, and maybe the object on the bottom might be metal. Okay, but they're both the same size. The basic idea is this, and we'll change it. Let's go for some green ink here. This object here has positive, and the word we're going to use is buoyancy. So it's positively buoyant, and of course you should probably figure out that this one is negatively, oops, that should be an E, buoyant. Negatively, oops, I changed my wording there. So negatively buoyant, positively buoyant. Okay, so the word we're talking about is buoyancy. And what causes buoyancy is force. Force is just anything. It's, you probably heard about it in the past as like a push or a pull, something that forces something in one direction or another, okay, or resists the movement of something in one direction or another. So what does that actually mean? Well, what it actually means is, again, if we have our beaker, and I'm going to draw in the beaker here, we're going to go back to our water. Here's our water. And let's say in the middle, I'm going to draw this box right here. And this object, let's say it's in the water at that depth. It's not at the surface, it's not at the bottom. Maybe it's kind of like our Flinker lab. Here's the deal. The deeper you go, the more pressure you experience. And pressure is just another way of experiencing a force. All right? And if you think about it, if you look at a point right here, let's say, I'm going to say point A is right here on the top, and let's say point B is right here on the bottom. Now, even though you look at an object or a person in the water as one thing, if you think about it, any object with 3 dimensions has a part of it that's higher up or shallower in the water than the rest of it. So, if you can guess at which point is this block experiencing the most pressure, i.e. the most force? Time's up. If you guessed B, you are indeed correct. All right, you can give yourself a big pat on the back. Because B, okay, B is lower and deeper. Okay, so there's going to be more force. If I were to draw the force arrows, we have a larger arrow coming up from the bottom because you have more pressure, more force on the bottom. Then I'm going to draw a shorter arrow up on top than force coming down from the top, like gravity, okay? Whatever it's going to be. So the force on the bottom is going to exceed the force on the top. Why? From the force of the water, there's less pressure, okay? So that means that whenever an object is in water, you always have a greater force pushing up from below. So you're saying, well, if that's the case, why do things sink? Gets a little more complicated, gets into a concept called density, but basically the idea is if this brown object here, this block of whatever it is, if its combined density and its mass overcomes that force that's pushing up from the bottom, it will sink. If it is less than the force that is pushing up from the bottom, it will float. And if it directly equals it, just like our Flinker lab, it will achieve what we call that neutral buoyancy and hang in the middle, okay? But one thing to remember is there's always a greater force at the bottom. So if you're hanging in the water, and I'll draw you now, let's say this is you. So if this is you sitting in the water, okay, and you are looking to decide what part of your body is experiencing more force, the same thing applies. Up here, and I'm going to switch colors, and I'm going to go to like purple now. Like point A would kind of like be your head. Point B would be your feet. All right, so the same thing applies. If you're hanging, upright in the water like that, your head will be experiencing less force than will your feet. All right, and that's why you feel lighter in the water, because you are positively buoyed. Okay, so that's the basis for why Archimedes' principle works. Remember, there's some more math. We'll get into that later. Based on what you're going to be doing, one more time, here's our beaker. Okay, here's our water. Oops. Okay, if an object is floating, that means, if you notice, some of the object is underwater, but some of it is above water. So if I have another object, let's say it's the same size, but it is sinking, it's denser than water, I have to think, well, let's look at the lab that we did, and let's say there's a little overflow spout right here, okay, where as I put the objects in the water, the extra water will flow out. How much water am I going to catch? Okay, well, if I have a little beaker here to catch the water that comes out, let's say this is object A, and this is object B, okay? If an object is going to sink, I think you may have already heard this in the past, that whatever the volume of that object is, it's going to displace an amount of water equal to its volume. So let's say in some way we calculated, and that's, by the way, if you have some kind of irregularly shaped object and you don't know how to find its volume, the easiest way to do that is to put it into a container of liquid and find out how far the level rises, the meniscus perhaps on a graduated cylinder, or just like in my diagram here, how much water pours out. Whatever the volume of the water is, that's going to be equal to the volume of B. Okay, so B is based on volume. Okay, and then whatever the volume of the water is, I can measure its mass, and then it's appropriate. If I wanted to find that out, but that's not necessary. So if an object sinks, it will displace an amount of water equal to its volume, because the whole thing is underwater. Now, I think you can tell that A won't be doing that, okay, because A is not completely underwater. So how much water will A displace? Well, A will displace an amount of water equal to its mass, okay? So for an example, if A weighs 2 grams, let's say A weighs 2 grams, then 2 grams will be how much water will be going into the catchment beaker. Okay. Similarly, if B, let's say, is 10, let's say it's a 10 milliliter volume solid, then 10 milliliters is what's going to go overflowing into the beaker. Okay, so remember that objects that float displace an amount of water that's equal to their mass, and objects that sink displace an amount of water equal to their volume. And we'll go into later why that is true, but for now, that's the relationship that you're looking for. Okay? Catch you next time.